so it was way too big. The calculator couldn't handle it. Okay, in many cases, it is useful to approximate a discrete distribution with a continuous distribution. In particular, we often use the normal distribution to approximate the binomial distribution. Notice how they were the same shape in that last problem? Okay, the one should have had 68% between plus or minus 1 standard deviation. It had 67.3. Should have had 68. Pretty good approximation. All right. Historically, this is because we didn't have calculators. But even now, if we get an icky enough problem, our calculators can't handle it. Okay? So, never mind. All right. So this is appropriate when p is close to 1/2 and you have a lot of people you're trying this on. So turn your page. You're going to have these graphs. Okay? It fits with your dice example. This is a picture of a binomial distribution if, let's say, you rolled the die 10 times. Okay? It looks like this. If you rolled the die 30 times, notice how much better it fits a binomial distribution. So it fits, the closer the probability of success is to 1/2, and even more important, the number of trials you're doing. If you're only doing 5 trials, you probably shouldn't use a normal distribution to approximate it because it's not going to look very normal. But if you're doing 30 or more, it might start to look normal. And actually, they're saying, here's how we test for it. We're going to take the number of trials times the probability. And we want that to be greater than or equal to 10. So if we want to use the normal approximation when p is close to 0, so p isn't 1/2, it's not flipping a coin. Okay, instead it's maybe 1/8 or 1/10 probability of success. We need to have at least 3 standard deviations below the mean before we can't have any successes, right? If the probability of success is skinny, okay, we still need to be able to go 3 standard deviations below the mean before we get into negative trials or negative probabilities. So we need the mean minus 3 standard deviations to still be a positive number. Well, this is the mean formula. This is the standard deviation formula for a binomial. If you do algebra, you find out in order to make that happen in general, the number of trials times the probability of success needs to be bigger than 9. So we will check n times p being greater than or equal to 10 before we can use a normal to approximate a binomial. That means on your tests and stuff, if that's greater than 10, you could use either one and still get full credit. And both answers are going to be really close, if not the same. Okay, so it says, let's use the binomial approximation to approximate the original answer for the one the calculator couldn't. X is the number of 6's, and x is approximately binomial distributed. We need to find the probability of x being greater than 167,000. So we're going to turn it into a normal. To do this, I need to find the mean and the standard deviation. Okay, well, mean is given by n times p, and standard deviation is given by this. So I'm going to do 1,000,000 trials with a 1/6 chance of success. That's my average. Okay, I'm going to use 1,000,000 divided by 6 in my calculator, so there's no rounding error. And I'm also going to just type this directly into my calculator. That's NPQ, so there's no rounding error. And then just like with the normal curve, I draw my picture. Okay, so you should have had this written down. Now let's look at it. Guys, so we now have, like 2 units ago, we have a nice normal curve with the mean given by this, right? And a standard deviation given by this. And we want the probability of it taking more than 167,000. So from here up. And now we're just going to use norm CDF. 167,000 to infinity. Notice that I type it in, and instead of getting an error, the calculator can handle a normal because it doesn't have all those choose functions. That's the difference. It's not doing 1,000,000 choose 1 million choose 2. It can handle it. It's about 18.6% chance of it taking that many. Suppose that 51% of US residents are women. In a random sample of 1,000, what is the probability that fewer than 500 women are selected? Use the binomial model and the normal approximation and compare results. So for the binomial model, 1,000 with a probability of picking a woman of 0.51, okay, X equals the number of women, and we want the probability of it being less than 500 women. So we randomly pick 1,000 people. What's the chance of getting less than 500 women if 51% of the population is a woman? So that would be the same as having 0 women, 1 woman, okay, 1 woman, up to 499 women. So again, you could do 1,000 women choose 0, 1,000 people choose 0 women, up to 1,000 people choose 499 women, or binom CDF. All right, so you should write all of this down so that you have the theory, but on your homework, you could just put this part. You need to define what you're doing and this part with the answer. Now we got that answer. Now let's see if we could do it the other way. We need to check to see if it could be normal. So we need to check the NP is greater than or equal to 10, and also the NQ is greater than or equal to 10. It's called the success failure condition. Probability of success, probability of failure. Well, if I did the NP, that's greater than 10, and Q is greater than 10. Notice the number is written in. You have to write the number in. You cannot just say NP is greater than 10. AP will give you 0 points for that. They are looking for 510 is greater than 10 and where you got it. Because that works, we can then use the formula to find the mean, okay, which was, again, 1,000 times the probability of success. And then this is the square root of NPQ. Now we can put that directly in our calculator. Notice it's lower bound, upper bound, mean, and standard deviation. And we got a very similar probability. So instead of 25.3%, we got 26.3 with our approximation. Again, the larger n is, and the closer p is to 1/2, the better fit. All right, in a sample of size 10, what is the probability that fewer than 5 women are selected? Use the binomial model and the normal approximation. So binomial model, X is approximately normally distributed, okay, out of 10 people and a 0.51% chance of being a woman. That's the probability of X being less than 5. Notice that I only have a 4 right here because we don't want the 5th. We want less than 5. Or if I did the normal to get the average, I did 10 times 0.51, and I did NPQ. Okay, they are fairly different. Why are they different? Sample size isn't big enough. It actually failed the success failure condition. Okay, the success failure condition, which again is NP greater than or equal to 10 and NQ greater than or equal to 10, it failed it. So we should not have tried to do it with the normal model. It's not close enough. So this shape actually probably was more like this than normal, which is why it messed up. So even though our calculator can handle any reasonable sample size, we need to use normal when we do inference procedures in future chapters. You guys don't care about that. So be careful. You always have to test the success failure condition, okay?